in the vast silence before anything had a name, before time could be counted or light could pour across the emptiness. The universe existed only as an idea on the edge of becoming. It was a moment concealed from all future witnesses, a moment that no chronicle of kings or empires could preserve, a moment before history itself had the luxury to begin. And then, without warning and without precedent, reality erupted from a point so small it defied the meaning of space, unfolding in a storm of energy so fierce that its echoes would one day sculpt the stars, the worlds that cradle life, and the galaxies that sweep like celestial cities across the night. In that blistering newborn cosmos, where temperatures soared beyond imagination and the laws of physics twisted into shapes they would never again assume, the seeds of all future structure flickered in and out of existence, and the first whispers of order stirred beneath the chaos. As the universe expanded and cooled, falling from impossibly high temperatures toward states where particles could survive more than a heartbeat, tiny ripples of density, minute wrinkles in the fabric of matter and energy, began to imprint themselves across the cosmic landscape. These wrinkles were not accidental blemishes, but the crucial imperfections without which the universe would have remained an endless, formless mist. It is from these fluctuations, born from the earliest quantum tremors, that every great cosmic architecture would later arise. They were the fingerprints of creation, stamped onto space-time itself when the universe was still an infant, destined to become the skeleton upon which galaxies would anchor their spiraling arms. The universe in these first minutes was a forge more ancient and more intense than any star, fusing the simplest elements in a cosmic alchemy that produced vast oceans of hydrogen, helium, and traces of lithium. Though these elements were pristine and unrefined, they carried the potential to ignite the earliest stars, the first sources of illumination in a cosmos still adrift in its own infancy. Yet despite this celestial abundance, the universe remained dark. For hundreds of millions of years, no star burned, no galaxy spun, and the vast reaches of space were drenched in a darkness so complete that even the memory of the early blaze faded into a cold twilight. During this long night, something invisible to future human eyes took command of the universe's fate. Dark matter, that mysterious and elusive substance that neither reflects nor absorbs light, began to gather silently into immense halos. These halos, gravitational wells carved out by forces no early atom could resist, became the first great structures in the cosmos. They were vast scaffolds made not of solid stone or metal, but of something far stranger, something that only revealed its presence through the tug of gravity. Within them, ordinary matter, mere baryonic dust compared to the enormity of dark matter, began to fall inward, drawn by the promise of eventual ignition. The pull of these halos was patient but relentless. Over tens of millions of years, gas drifted inward, cooling as it collapsed, forming immense clouds dense enough to ignite the first stars. These stars were unlike any that would exist billions of years later. They were giants, titanic, blazing entities composed entirely of the primordial elements. They burned with temperatures and luminosities that strained the limits of stellar physics, living brief, furious lives before detonating in spectacular supernovae that shook their early galaxies and flooded space with the first heavy elements. These heavy elements, carbon, oxygen, iron, would eventually become the raw material for future stars, planets, and the biological stories that would unfold on distant shores of time. But in this early era, long before the Milky Way unfurled its spiral arms, or the first galaxies acquired familiar shapes, the universe was a patchwork of tiny, fragile structures. These protogalaxies, some no larger than small star clusters today, flickered like ghostly lanterns in the dark seas of the cosmos. They collided often, merging and tearing one another apart, exchanging stars in gravitational dances that would ultimately decide their fates. Every collision left scars, stars thrown into intergalactic space, gas compressed into the birth of new stellar generations, dark matter halos twisting into new configurations. Yet from this turbulent era emerged the foundations of the first recognizable galaxies, the grand cosmic institutions that would shape the next 13 billion years. As time marched onward, and as the universe expanded steadily into the vastness it would eventually claim, the earliest galaxies began to grow. They were hungry entities, devouring the smaller ones that drifted too close, accreting cold gas from the cosmic web, and weaving intricate tapestries of stars across their widening disks. Every merger rewrote their histories, altering their structures, inducing bursts of star formation, and feeding the supermassive black holes that were beginning to stir in their centers. How these black holes formed so early remains a mystery that challenges modern astrophysics, yet their influence was unmistakable. Their gravity sculpted the motion of stars. Their jets and winds regulated the growth of galaxies, and their enigmatic presence gave each galaxy a gravitational heart around which the grand spirals and luminous halos could gather. It was during this period of cosmic adolescence that galaxies began to diverge into the diverse forms that future astronomers would classify with reverent curiosity. Some grew into beautifully ordered spirals, their disks cooling and settling into elegant patterns of arms that would swirl like celestial whirlpools. Others became ellipticals, massive, swollen structures with stars moving in random, chaotic orbits, relicts of ancient mergers that had erased all memory of order. Still others remained irregular, their shapes twisted by gravitational forces, collisions, or violent bouts of star formation. Each galaxy carried a unique biography, written in the motions of its stars and the chemical makeup of its gas, a biography shaped not by a single event, but by billions of years of cosmic weather. Through all of this, gravity remained the master architect. It guided the flow of gas along the filaments of the cosmic web, a vast network of matter that stretched across the universe like a three-dimensional tapestry. These filaments connected clusters of galaxies, forming superclusters, immense congregations of thousands of galaxies bound together in titanic structures that dwarfed every human conception of size. Inside these clusters, galaxies were not solitary wanderers, but members of immense cosmic communities, interacting, struggling, and evolving over millions of years. The densest regions became arenas of frequent encounters where galaxies shaped one another through tidal forces and high-speed collisions. Meanwhile, galaxies in the quieter outskirts grew more serenely, tracing graceful arcs around the cluster's center while steadily accumulating matter. By the time the universe reached several billion years of age, the rate of star formation across galaxies had surged to its cosmic peak. Stars ignited by the trillions, filling galaxies with light and weaving bright threads into the cosmic fabric. This epoch of brilliance transformed the appearance of the universe, turning dark halos into glittering islands of starlight. Dust born from dying stars drifted through interstellar space, providing the seeds for planets and the intricate chemistry that would one day lead to the possibility of life. But for now, the universe cared only for its relentless expansion and the ceaseless evolution of its galaxies, structures that grew more complex and more diverse with each passing 100 million years. And yet, as galaxies matured, so too did the cosmic stage they inhabited. The universe continued to expand, stretching the distances between galaxies and cooling the intergalactic medium. The once frequent collisions between young galaxies became rarer for those living in the cosmic countryside, though in crowded clusters, the dance of interactions remained lively and unpredictable. Some galaxies, stripped of their gas by the fierce conditions within clusters, ceased forming new stars and began to age quietly, their once bright populations fading slowly over billions of years. Others, blessed with reservoirs of cool hydrogen, continued to fire new stars in their spiral arms, their rotation maintaining the elegant patterns that would awe celestial observers in distant future epochs. Yet even as galaxies diversified into spirals, ellipticals, dwarfs, and irregulars, they all bore the imprint of the same primordial story, a story written long before the first star ignited. Their shapes, their motions, their star-forming histories, all of it traced back to the earliest fluctuations in density, to the gravitational pull of dark matter halos, and to the conditions forged in the first few moments after the Big Bang. Each galaxy was a monument to the universe's own memory, a record of interactions, collisions, and the deep physics that governed the growth of structure in an expanding universe. And as billions of years continued to unspool, these galaxies would become the cradle for countless systems of planets, nebulae, and stellar remnants, each contributing to the greater cosmic symphony that had begun before time had a language.
In the quiet depths of intergalactic space, far from the bustling cores of rich clusters where galaxies crowded together like ancient cities pressed against their own walls, vast stretches of cosmic solitude gave rise to a different kind of evolution. Here, galaxies were not shaped by violent encounters or tidal distortions, but by the slow, persistent sculpting of cosmic filaments that threaded through the void. These filaments, faint and ghost-like, yet unimaginably immense, carried cool streams of hydrogen that flowed like silent rivers into the hearts of developing galaxies. This cold accretion, a process invisible to early human telescopes, but fundamental to the structure of the universe, fed galaxies with the lifeblood of new stars. Through these hidden channels, galaxies grew in mass and complexity, maintaining their luminous vigor even as the universe marched toward greater emptiness. Within many of these isolated galaxies, star formation progressed in cycles, driven by the interplay between gravity and gas, and the feedback from generations of stars that lived and died within their bounds. As gas clouds collapsed under their own weight, stars ignited in luminous clusters, each cluster wrapped in the glowing remnants of the nebula that birthed it. But the very stars that brought brilliance to their galaxies also sowed the seeds of transformation. Massive stars lived briefly, burning through their nuclear fuel with ferocity. And when they perished in supernova explosions, shock waves raced outward, compressing nearby gas into new star-forming regions, while also blasting other pockets of gas into the galactic halo. In this turbulent cycle, galaxies developed intricate internal rhythms, patterns of creation and destruction that over millions of years carved their luminous structures into the forms seen by distant astronomers. Yet star formation alone could not explain the evolving character of galaxies. At their cores, hidden behind clouds of dust and wrapped in the gravitational embrace of millions of stars, supermassive black holes began to awaken. Their origins, born in the earliest epochs of cosmic history, when dense pockets of gas collapsed at astonishing rates, remained a puzzle that decades of research had only partially deciphered. But their influence was unmistakable. For as these black holes accreted matter, they unleashed torrents of energy that spread throughout their host galaxies. Sometimes this took the form of narrow jets that pierced the galactic halo, streams of relativistic particles traveling vast distances across intergalactic space. At other times, it emerged as fierce winds that heated surrounding gas and slowed the birth of new stars. These black holes, silent for long periods, and then suddenly roaring with unimaginable power, acted as regulators in a cosmic drama where too much or too little star formation could alter the entire destiny of a galaxy. Some galaxies, especially the most massive ellipticals that formed in crowded environments of ancient clusters, bore the imprint of this regulation clearly. Their central black holes grew to enormous sizes, and the energy they emitted prevented fresh gas from cooling and settling into star-forming disks.
As a result, these galaxies aged into giant reddish spheres populated by old stars whose light dimmed gently with time. Their shapes, once shaped by brutal mergers and violent collisions, now remained steady, sculpted into smooth ellipsoids that resembled enormous celestial relics. Within them, the histories of multiple galaxies were preserved, stitched together by ancient gravitational dances that had long since faded into silence. But in quieter regions, spirals maintained their elegant forms, rotating like vast celestial pinwheels around their central bulges. The dynamics of these systems, governed by the distribution of mass within their disks and the mysterious dominance of dark matter in their halos, produced consistent rotational patterns that perplexed early astronomers. The outer regions of these spirals moved far faster than expected, based on visible matter alone, suggesting the presence of an invisible mass that outweighed the combined light of billions of stars. This observation, once controversial, became one of the strongest pieces of evidence for the pervasive influence of dark matter in shaping galaxies. It was a reminder that even the most luminous structures in the universe were guided by forces hidden from direct observation, forces that had shaped their origins and governed their destinies since the dawn of time. As spiral galaxies aged, their arms traced patterns of density waves that moved through their disks like ripples across the surface of a pond. These density waves, rather than fixed structures made of the same stars, acted as gravitational patterns that swept through the disk, compressing gas and triggering star formation along their paths. In this way, the spiral arms remained visible for billions of years, illuminated by generations of young, massive stars that lived briefly and brightly. Behind them, older stars drifted outward, contributing to the diffuse glow of the disk. This process revealed that spiral arms were not static masterpieces etched permanently into the galactic canvas, but living, shifting expressions of the galaxy's inner dynamics. The growth of galaxies, however, was not limited to their internal processes. Across the vast cosmic web, galaxies continued to interact in subtle and not-so-subtle ways. Even when separated by hundreds of thousands of light-years, their gravitational influence could stretch across space, creating tidal bridges and streams that connected them like invisible strands. When galaxies passed close to one another, these forces could distort their shapes, pulling out long tails of stars and gas that formed tidal streams. These streams, sometimes extending for tens of thousands of light years, preserved the memory of past encounters long after the galaxies themselves had moved on. By tracing these stellar streams, astronomers in distant epochs could reconstruct the ancient interactions that had shaped their galaxies, reading them like archaeological layers in a cosmic landscape. Among the smallest galaxies, the dwarfs that drifted through the halos of larger systems, such interactions were common. Dwarf galaxies, though modest in size and mass, played a crucial role in the evolution of larger galaxies by delivering fresh supplies of gas and stars through mergers. Many of the stars in the halos of massive galaxies were once members of these dwarfs, scattered into new orbits when their original homes were torn apart by tidal forces. Over time, these scattered stars formed vast stellar halos that extended far beyond the visible disks, so faint that only the keenest modern telescopes could detect them. These halos acted as living records of the billions of years during which galaxies consumed their smaller neighbors, growing not through steady, gradual accretion alone, but through dramatic acts of cosmic cannibalism. As galaxies continued to evolve, the large-scale structure of the universe itself underwent transformations. Superclusters grew more distinct, their shapes molded by gravitational attraction along cosmic filaments. Meanwhile, vast voids expanded between them, regions of space so empty that a traveler crossing them might journey millions of light years without encountering a single bright galaxy. These voids were not mere absences, but essential components of the cosmic architecture, created as matter flowed toward denser regions and left behind expanses of profound isolation. Their existence testified to the universe's continual expansion, a process driven by dark energy, the enigmatic force that accelerated the growth of space itself. As dark energy became increasingly dominant, galaxies drifted farther apart, reducing the frequency of encounters and altering the future course of galactic evolution. Although the age of rapid galaxy formation had long since passed, the universe remained alive with processes that reshaped galaxies in subtle and powerful ways. Gas inflows from the cosmic web continued to replenish the disks of some spirals, allowing them to maintain steady rates of stellar formation. In other galaxies, internal instabilities redistributed matter, forming bars and rings that channeled gas toward the center and fueled bursts of stellar activity. In regions where galaxies clustered, interactions continued to strip gas from their outer regions, transforming spirals into lenticular systems with faint disks and exhausted star-forming reservoirs. Each galaxy, shaped by its environment, followed a path influenced by its mass, history, and the cosmic neighborhood it inhabited. Still, even as new stars continued to form, the overall trend across the cosmos pointed toward gradual decline. The reservoirs of cool gas that once fueled star formation became scarcer as galaxies aged, and the processes that once replenished them slowed dramatically. Some of the gas was heated by energetic feedback from stars and black holes, making it too warm to collapse into new stars. Other clouds were consumed by previous generations of stellar birth, transformed into the glowing populations that now illuminated the galactic disks. This slow depletion marked a turning point in the universe's history, signaling the transition from an age of vibrant creation to one of gradual dimming. But the galaxies themselves, shaped by billions of years of cosmic events, continued to tell stories written in starlight. Across the next billions of years, as the universe entered its middle age, the galaxies that once blazed with fierce youthful brilliance settled into slower rhythms. Yet their grandeur lost none of its scale or complexity. In the spiraling arms of countless star systems, new generations of stars continued to emerge from cool molecular clouds, illuminating their dusty cradles with soft ultraviolet light. These glowing nurseries, dense with gas shaped by magnetic fields and turbulence, produced stars of every conceivable size, from red dwarfs destined to smolder quietly for trillions of years, to blue giants whose ferocity would sear surrounding space for only a brief cosmic moment. Within these same nebulae, intricate dances of molecular chemistry fashioned the building blocks of planets, comets, and potentially life, planting seeds of future stories that would unfold across continents of time yet to be written. Still, even as star formation occurred within these vibrant nurseries, the dynamics of galaxies shifted subtly with age. Many spirals developed central bars, elongated patterns of stars that stretched across their cores, rotating as unified structures under the guidance of gravitational resonance. These bars acted as engines that funneled gas inward, where it collected in swirling rings near the galactic nucleus. Such inflows often triggered intense regions of star formation, or, when conditions allowed, fed the central black holes, briefly awakening them from slumber. In a few rare moments, the heart of a galaxy would flare with renewed energy, becoming an active galactic nucleus whose brilliance rivaled that of billions of stars. These eruptions, though temporary on cosmic scales, sculpted the flow of gas throughout the disk, gently bending the evolution of the entire system. Elsewhere in the cosmic expanse, galaxies lived out quieter fates. Lenticular galaxies, systems that straddled the boundary between spirals and ellipticals, drifted through space like ancient ships bereft of wind. Their disks, smoothed by past interactions or deprived of star-forming gas by cluster environments, displayed little of the spiral structure that once defined them. The stars within moved on predictable orbits, creating soft, featureless glows that reflected histories marked by slow depletion rather than violent upheaval. And yet, even in their seeming inertness, these galaxies were anything but inert. Subtle resonances shifted their internal dynamics. Faint shells and ripples, visible only in deep exposures, preserved the scars of past encounters. Their quiescence was not a lack of history, but the quiet after the story's loudest chapters had passed. Far more chaotic were the galaxies that lived within the dense cores of massive clusters, where the gravitational pull of thousands of neighbors wove a relentless tapestry of interactions. Here, galaxies raced past one another at tremendous speeds, their motions guided by the collective gravity of an entire cluster bound within a titanic dark matter halo. The intergalactic medium in these regions was heated to extraordinary temperatures, forming a thin X-ray emitting plasma that flooded the cluster like a ghostly sea. Galaxies plunging through this medium experienced pressures that stripped their gas in sweeping arcs, leaving behind long luminous tails resembling cosmic jellyfish. These stripped galaxies, deprived of their star-forming fuel, gradually faded into redder, quieter systems. Meanwhile, the lost gas mixed with the cluster's hot atmosphere, contributing to the glowing haze that revealed the cluster's immense gravitational reach. Even the motion of galaxies within these clusters spoke of ancient events. Many clusters originated from the merging of smaller groups, collisions that unfolded over billions of years. As these groups coalesced, their galaxies clashed, their dark matter halos intermingled, and shock waves rippled through the hot plasma, leaving signatures etched across millions of light years. In the aftermath of these colossal mergers, the largest galaxies in the universe often emerged at the centers, brightest cluster galaxies, monstrous ellipticals swollen by countless meals of smaller companions. Their halos extended far beyond their visible boundaries, encompassing tens of thousands of globular clusters and weaving together stellar streams left behind by the many galaxies they had absorbed. These central giants stood as cosmic monarchs, reigning over clusters with masses that dwarfed anything found in quieter corners of the universe. While some regions of the cosmos teemed with such activity, others slipped into deeper isolation. In the expansive voids that sprawled between superclusters, lone galaxies drifted without the companionship of neighbors, their fates dictated almost entirely by internal processes and the slow, steady inflow of gas from their surroundings. Such galaxies lived unhurried lives, forming stars at modest rates and evolving with tranquil stability. Their isolation protected them from disruptive encounters, but it also denied them the bursts of star formation triggered by gravitational interactions. Over time, many became simple, stable spirals or mellowed out into faint, extended disks, their structures influenced by the smooth gravitational field of the void. These galaxies, though humble in appearance, offered insights into the universe's most pristine conditions, tracing evolutionary paths unmarred by cosmic violence. Yet, regardless of location, cluster, filament, or void, every galaxy felt the growing influence of dark energy, the enigmatic force that drove the accelerated expansion of the universe. As space stretched ever more rapidly, galaxies drifted apart with increasing speed. The cosmic web that once pulled matter inward now found its filaments stretched thinner across the expanding universe. In time, even the gravitational bonds of larger structures began to loosen. Superclusters, once expected to survive indefinitely, faced the prospect of eventual separation into isolated islands of galaxies whose horizons would shrink as distant structures receded beyond visibility. The cosmos, in its youth, a lively and interconnected network of matter, slowly transitioned toward a future where vast distances would conceal once close neighbors behind veils of unreachability. In this changing landscape, star formation across the universe gradually declined. The cosmic era known as cosmic noon, a time when galaxies burned with vigorous creation, drew further into the past. The supply of cold gas diminished as fewer streams from the cosmic web reached galactic disks, and internal processes consumed or heated the remaining reservoirs. In spiral galaxies, the brightest star-forming regions dimmed as their molecular clouds dispersed. In ellipticals, older stars continued their long descent into lower luminosity as their nuclear fuel waned. The galactic population as a whole aged, painting the universe in subtler hues than the brilliant ones that characterized its earlier days. Even so, galaxies remained dynamic on scales both grand and delicate. Within them, small pockets of star formation persisted in sheltered regions, and interactions, though rarer, still breathed new life into those that collided or passed close enough to exchange gravitational tugs. The Milky Way itself, a spiral galaxy in a quiet corner of the cosmic web, continued to grow slowly by drawing in dwarf galaxies and gas clouds from its halo. Its spiral arms wound steadily around its core, illuminated by stellar associations and dotted with massive molecular clouds. Far beyond its disk, its faint stellar halo testified to ancient mergers, while its central bar gently guided gas inward to sustain intermittent bursts of star formation in the galactic center. Not far beyond the Milky Way's gravitational influence, the Andromeda Galaxy journeyed toward its eventual meeting with our own. This future collision, slated to unfold billions of years ahead, represented a familiar phase in the life of galaxies, the slow, graceful merging of two spiral giants into a new, more massive elliptical system. Such events had occurred countless times across the cosmos, shaping galaxies throughout their histories. When Andromeda and the Milky Way finally intertwined, their stars would largely pass through one another unscathed, due to the vast distances igniting fresh waves of star formation that would briefly rekindle the brilliance of youth in the aging universe. Their dark matter halos would merge first, knitting the two galaxies together long before their stellar disks coalesced, and over billions of years, the once separate spirals would settle into a single, more spheroidal shape, reflecting the cumulative gravitational sculpting that defined their union.
Such mergers, whether gentle or cataclysmic, formed the backbone of galactic evolution. In their aftermath, new structures emerged, rings of stars created by radial oscillations, shells formed by the debris of dwarf galaxies consumed by larger hosts, or elongated streams that wrapped around galactic halos like cosmic signatures. These remnants preserved the memory of events long past, encoding histories that careful observers could decode billions of years later. In this way, galaxies served as living archives of the universe, bearing within their structures the long and intricate narratives of matter shaped by gravity, time, and chance. As the ages advanced and galaxies followed the trajectories laid out by their ancient dynamics, the universe settled into patterns that seemed almost contemplative compared to the violence of its youth. Yet beneath this outward calm, invisible processes continued to sculpt the fates of galaxies with the same persistence that had shaped them since their dawn. In the vast halos surrounding every galaxy, dark matter remained the dominant force, creating gravitational landscapes that extended far beyond the regions where starlight could reach. Within these halos drifted streams of debris from swallowed companions, thin, ghostly currents of stars that traced the wandering paths of long-vanished dwarfs. Over time, these streams fanned out, wrapping themselves around their new hosts like faint ribbons whose presence betrayed the restless past of even the most tranquil galaxy. In the disks of spiral galaxies, subtle gravitational resonances shaped patterns that repeated across billions of years. The interplay between orbiting stars, gas clouds, and the galaxy's overall mass distribution created shifting waves that moved through the disk at speeds distinct from the stars themselves. These waves gathered gas into elongated arms that appeared to wind perpetually around the galactic center, yet the stars that illuminated them simply passed in and out of the pattern, giving the illusion of permanence. Molecular clouds drawn into these arms compressed into clumps dense enough to collapse into new stars. Around some of these stellar nurseries, the combined radiation of massive stars carved out cavities into the surrounding gas, hollowing out bubbles that grew and merged into superbubbles spanning hundreds of light years. These structures, often unseen except in the glow of ionized gas, revealed the powerful influence that even small groups of stars could exert on the broader galactic ecosystem. Meanwhile, in the halos of galaxies both large and small, globular clusters drifted along ancient orbits. These densely packed star clusters, among the oldest in the universe, were relics of the earliest eras of galaxy formation. Their stars had been forged in conditions radically different from those of later epochs, enriched only by the faintest traces of elements heavier than helium. The cluster's internal dynamics, shaped by countless gravitational encounters between their stars, preserved tight-knit structures that had survived tidal forces, galactic mergers, and the slow erosion caused by encounters with passing molecular clouds. Some globular clusters carried within them the chemical signatures of multiple stellar generations, offering clues into the complex and sometimes turbulent pasts that had forged them. Though small compared to the galaxies they orbited, their resilience made them among the most durable witnesses of cosmic history.
Beyond individual galaxies, entire groups evolved in patterns dictated by their shared gravitational bonds. Some groups remained loosely bound, their members drifting in wide orbits that kept them separate for long intervals. Others tightened into compact configurations where galaxies circled one another in close proximity, exchanging gas and stars in a slow but persistent dance. In some of the most ancient groups, the repeated gravitational interactions slowly stripped smaller galaxies of their gas and stars, leaving behind compact, quiescent remnants whose structures bore little resemblance to their former selves. These so-called ultra-compact dwarfs, remnants of galaxies once vibrant with star formation, now orbited their larger companions like carved gemstones eroded into new shapes by eons of tidal sculpting. Yet it was in the realm of galactic clusters, those immense gravitationally bound cities of hundreds or thousands of galaxies, that the universe displayed some of its most dramatic large-scale structures. In the cores of massive clusters, interactions were relentless. Galaxies lost gas to the hot intercluster medium. Their outer halos were eroded by tides, and their motions traced orbits governed not by individual interactions, but by the deep gravitational well of the cluster itself. Shock waves rippled through the hot plasma as subclusters merged, generating colossal arcs of radio emission where electrons spiraled along magnetic field lines. These radio relics, as modern astronomers would later call them, stretched across millions of light years, testifying to the magnitude of the forces involved. They were the after-images of enormous cosmic collisions, drawn in glowing outlines upon the dark canvas of space. Amid these vast environments, the brightest cluster galaxies grew to extraordinary sizes through successive mergers with smaller neighbors. Their extended halos often blended into the intercluster light, a diffuse glow produced by stars that had been stripped from their home galaxies and now drifted freely within the cluster. This intercluster population, though faint, contained countless trillions of stars, each one a wanderer, tracing an orbit determined by the gravitational geometry of an entire cluster. Over time, these stars stretched into arcing paths, forming smooth envelopes of light around the cluster's center. Their existence underscored the immense scale of galactic interactions and the deep history of assembly that formed the clusters dominating the cosmic landscape. While some galaxies thrived in these bustling environments, others were slowly transformed by encounters with the intercluster medium. Spirals entering a cluster for the first time often encountered a force known as ram pressure stripping. As they plunged through the hot plasma at tremendous speeds, this medium swept away their outer gas layers, creating luminous arcs that streamed behind them like tails. Deprived of their star-forming fuel, these galaxies evolved into shapes dominated by older stellar populations, losing the vibrant blues and pinks of young clusters and fading towards softer yellows and reds. The process could happen quickly on cosmic timescales, turning vibrant systems into passive ones within a few 100 million years. In this way, clusters acted as engines of transformation, altering the galactic population and accelerating the aging of galaxies caught within their depths.
Yet despite the dominance of clusters and filaments in shaping the universe, the majority of galaxies lived in far quieter settings. In these environments, internal processes dictated their evolution to a far greater extent. Some spirals developed warp-like distortions in their outer disks due to the gravitational influence of their halos or minor mergers with faint companions. Others grew rings of gas and stars formed by resonances within the disk or by the gentle infall of gas from the cosmic web. These rings, sometimes nearly perfect in their symmetry, glowed with bright star formation and offered striking signatures of a galaxy's internal rhythms and the silent currents of its environment. Even dwarf galaxies, seemingly humble in mass and luminosity, displayed rich internal dynamics, patchwork patterns of star formation, winds from massive stars shaping their gas, and tidal interactions with larger neighbors, carving out long trails of stars that drifted into halo populations. Over time, galaxies carried the cumulative signatures of these processes forward through the ages. Their chemical compositions changed as successive generations of stars enriched the interstellar medium with heavier elements. Their stellar populations aged, shifting the balance from luminous, short-lived stars to cooler, longer-lived ones. In some galaxies, bursts of star formation, triggered by mergers or internal instabilities, added new layers to their histories, each one marking an epoch with its own distinct chemical and dynamical character. By studying these populations, future observers would be able to reconstruct the evolutionary pathways of galaxies, reading their histories encoded in gradients, populations, and the motions of their stars. As the universe continued its expansion, the distances between galactic groups grew larger, and the cosmic web stretched across an ever-widening stage. But expansion alone did not erase the structures that had formed. Instead, it froze them in place, locking galaxies into islands of matter whose interactions were confined to scales small compared to the ones that once dominated the cosmos. The universe, once a cradle of rapid assembly, became an expanse where galaxies illuminated the darkness but drifted ever farther apart. In this new environment, isolated galaxies would continue to evolve internally, while clusters remained bound by gravity's enduring grip. Even in this era, the universe did not stand still. Supernova explosions continued to enrich the interstellar medium. Black holes in galactic centers accreted matter sporadically, producing bursts of radiation that illuminated immense distances. New stars formed from collapsing clouds, while others aged into white dwarfs, neutron stars, and black holes. On every scale, galaxies persisted as theaters of creation and transformation, carrying forward the long narrative of cosmic evolution begun in the first fraction of a second after the Big Bang.
Yet even as galaxies aged gracefully beneath the widening arc of cosmic time, the processes woven into their earliest epochs continued to echo through their structures. In the outer reaches of spiral disks, far beyond the bright lanes of star formation, diffuse regions of starlight extended into faintly glowing outskirts known as stellar halos. These halos were not coherent disks or spheres, but sprawling mosaics of ancient stars, some birthed within the galaxy itself, others torn from defunct companions long ago. Their orbits were paths of quiet eccentricity, stretched out and inclined, weaving through the galaxy's gravitational field like elder wanderers whose journeys told stories of forgotten collisions. In these outskirts, the influence of dark matter revealed itself through stellar motions that deviated from the luminous mass alone, hinting at the vast unseen reservoirs that enveloped every galaxy. Closer to the galactic center, the evolution of the bulge, whether a classical one born of violent mergers or a boxy, elongated structure shaped by the internal dynamics of bars, offered clues about the galaxy's earlier chapters. Classical bulges, with their densely packed, randomized stellar motions, bore the imprint of early turbulent eras when mergers dominated. In contrast, boxy bulges carried the signature of disk instabilities, formed when bars buckled under gravitational torques and puffed into three-dimensional shapes. Both types housed some of the oldest stars in their galaxies, their chemistry a record of rapid early enrichment. In their midst, often lurking behind forests of dust and rivers of gas, supermassive black holes presided with silent authority, their gravitational influence extending across light years and subtly shaping the motion of surrounding stars. But the black hole's influence extended far beyond mere gravitational constraints. When fed by accreting gas, they entered active phases that unleashed energy on scales far surpassing the output of entire galaxies. These active nuclei, sometimes obscured by thick toruses of dust, radiated with ferocity across the electromagnetic spectrum. In the early universe, such quasars could outshine their host galaxies entirely, becoming visible across billions of light years. Their jets, propelled by magnetic fields wrapped around spinning black holes, pierced into intergalactic space with extraordinary coherence, carving cavities into the surrounding gas and influencing the temperature and density of the circumgalactic medium. As these jets expanded, they could regulate the host galaxy's evolution, preventing gas from cooling and collapsing into stars. In this way, black holes, paradoxical engines of both destruction and regulation, played a decisive role in the life cycles of galaxies.
Beyond the immediate confines of galactic centers lay the vast circumgalactic medium, an enormous envelope of hot ionized gas that extended well beyond the visible edges of galaxies. This medium acted as both reservoir and gatekeeper for future star formation, supplying cool gas through gradual inflows while also receiving matter ejected by supernova winds and black hole outbursts. Its structure was intricate, filamentary, dynamic, and shaped by magnetic fields, cosmic rays, and the motions of satellite galaxies. Within it drifted clouds of neutral hydrogen, some dense enough to collapse into future star-forming regions, others mere wisps stretched thin by tidal forces. The circumgalactic medium connected galaxies to the broader cosmic web, mediating their growth across billions of years. Only in recent centuries of human science would this faint gas halo be revealed, a discovery that added new layers of complexity to the understanding of galactic evolution.
Meanwhile, the story of smaller galaxies, dwarfs, irregulars, and ultra-diffuse galaxies unfolded with equally rich detail. Dwarf irregulars, often dominated by gas and dark matter, flickered with sporadic bursts of star formation triggered by internal instabilities or mild interactions. In many, stars formed in compact clusters that carved holes in their surrounding gas when their massive members exploded. Dwarf spheroidals, stripped of gas and left with only ancient stars, orbited larger galaxies like quiet relics of past assembly, their existence a testament to the transformative power of tidal forces. Ultra-diffuse galaxies, whose low surface brightness belied the vastness of their dark matter halos, floated like ghosts within clusters, surviving in environments that should have torn them apart. Their very presence challenged assumptions about how galaxies could maintain structure despite their fragile appearance. The interactions between galaxies and their satellites created patterns of motion that persisted long after the events themselves had faded into the background. Some satellites followed polar orbits, tracing arcs perpendicular to the disk of their host, while others aligned with the primary galaxy's plane. Their motions were shaped by the dark matter distribution, which influenced their precession and orbital decay. As satellites approached too closely, they shed stars into tidal streams, graceful arcs that wrapped around the host galaxy in great loops. These streams acted as markers of ongoing assembly, showing that even in the present epoch, galaxies continued the ancient process of consuming their smaller neighbors. Over time, as satellites spiraled inward due to dynamical friction, they merged with their hosts, contributing stars to the inner halo or bulge and adding their dark matter to the broader halo. On still larger scales, the cosmic web's architecture evolved slowly, its filaments thickening where matter continued to accumulate, while voids expanded in regions where mass had long since migrated outward. The filaments served as channels for gas and galaxies alike, guiding their motions along gravitational gradients that stretched across hundreds of millions of light-years. At the nodes of these filaments, galaxy clusters continued to grow, their mass increasing through accretion of groups and lone galaxies that fell inward along the cosmic highways.
These infalling groups brought their own histories, pre-processed galaxies already transformed by earlier interactions. As they joined the giant clusters, they added new layers to the cluster's complexity, creating substructures visible through gravitational lensing and X-ray observations. The cluster's gravitational pull bent the light from distant galaxies behind them, forming arcs and distorted images that revealed the distribution of dark matter within. The largest structures in the universe, superclusters, remained only loosely bound, their futures uncertain under the accelerating expansion. Though some regions possessed enough gravitational cohesion to resist expansion, others would eventually drift apart, their connections stretched across increasing distances. In tens of billions of years, even the nearest galactic groups beyond local gravitational bounds would slip beyond the cosmic horizon, leaving only the closest structures visible to observers in the distant future. This gradual separation marked a profound shift in the universe's character, a slow isolation of cosmic islands, where galaxies, once heirs to a broad and interconnected network, would find themselves surrounded by an ever-deepening darkness. Yet, despite this growing cosmic isolation, life within galaxies remained shaped by internal processes. In many systems, the slow settling of gas into central regions created compact disks where new generations of stars formed in tight, spiraling lanes. In others, the exhaustion of gas led to quiet aging, where only the dimmest embers of star formation persisted. Some galaxies developed kinematically distinct cores, central regions whose stars rotated differently from those in the outer parts, likely formed through mergers or gas accretion. These cores offered clues about ancient interactions that had reshaped the inner dynamics of galaxies. Elsewhere, massive star clusters migrated inward under the influence of dynamical friction, contributing to the growth of nuclear star clusters that closely orbited central black holes. These dense clusters, containing millions of stars within light years of the galactic center, represented some of the densest stellar environments in existence, influencing both star formation and black hole feeding cycles. In quieter corners of the universe, the most diffuse galaxies drifted through the darkness, illuminated only by the faint glimmer of their ancient stars. Their low density made them vulnerable to the slightest external forces, yet many survived for billions of years, their shapes preserved by the deep gravitational wells of their dark matter halos. Some contained extended HI gas envelopes far larger than their stellar components, reservoirs that might one day collapse into new generations of stars under favorable conditions. Others existed as relics of tidal interactions, assembled from material stripped from larger galaxies, their origins written in the chemical composition of their stars. These faint systems, though easily overlooked, offered insights into the smallest scales of galaxy formation and the delicate balance of forces that shaped them.
And still, amid this diversity, the threads of common origin ran through every galaxy. Whether massive or modest, ancient or still actively forming, each owed its existence to the gravitational imprints laid down in the first moments after the universe began. Those tiny fluctuations, amplified over eons, determined where galaxies would form, how they would grow, and whom they would encounter in their long journeys. The galaxies were not isolated stories, but chapters within a vast chronicle of structure formation that spanned the entire cosmos.